3. 3 marks. That is the exact number of marks standing between your current grade and your target top band grade on a single Cambridge Physics motion graph question. Just 3 marks, but they are needlessly thrown away by thousands of students every single exam session, all because they misinterpret what a curved line actually means. So no fluff today. We are securing those 3 marks right now.
Okay, so let's get straight into it. The most painful yet incredibly common mistake I see on paper after paper is the failure to distinguish between constant speed, changing acceleration, and terminal velocity when looking at a curved graph. Students see a curve going up, they quickly scribble down speeding up and just move on. Well, the examiner reads that, crosses it out, and you lose the mark. You absolutely have to tell the precise physical story of what that curve represents.
Now you might be sitting there thinking, but I read the textbook. Well, here is why ordinary revision actually fails you in the exam hall. Memorizing formulas without connecting them to a physical context, it's a total recipe for disaster under pressure. If you're just blindly memorizing equations, ignoring your axis labels, or kind of confusing distance with speed, the exam is going to catch you out. A graph isn't just a math problem. It's a real-world event frozen on paper.
Right, so here is your quick win framework. If you only remember one thing from this, let it be this exact breakdown. You always check your axis first. On a distance time graph, the gradient, the steepness of the line, equals the speed. A horizontal line means you are stationary. But the moment you shift to a speed time graph, the rules completely change. The gradient here equals acceleration. And a horizontal line, you aren't stopped. You're just moving at a constant speed. Mixing these two up is literally where dreams of top bands go to die.
And that brings us to rule number 2, which is honestly a bit of a superpower. Once you've checked your axis and realized you have a speed time graph in front of you, you can do something amazing. The total area underneath that graph line equals the exact distance traveled by the object. Whether you're calculating the area of a simple rectangle, a triangle, or some really complex compound shape under the line, you are extracting physical distance directly from speed and time.
Let's actually look at how this plays out in a real Cambridge-style scenario. We've got the absolute classic here, the parachutist speed time graph. Notice how it isn't just a simple straight line. The curve dramatically changes shape over the 70-second fall. It sweeps up, flattens out, drops sharply, and then flattens out again. Every single bend in this line represents a massive shift in the actual physical forces acting on the parachutist.
So look closely at the graph. What happens exactly at the 35-second mark? In a moment, I'll show you the terminal velocity examiner clue right at 35 seconds that flips the mark scheme completely. But first, you need the framework to decode the curve leading up to it.
Because you absolutely cannot just guess here. You need a system. This is the 4-step framework that converts raw graph data into a structured top-band Cambridge response. Step 1, identify the concept. What kind of graph are we dealing with? Step 2, extract the evidence. What is the gradient actually doing right now? Step 3, apply scientific reasoning. Link it to physics concepts like air resistance or gravity. And step 4, use examiner wording. Use the precise vocabulary they are hunting for in the mark scheme.
Okay, let's put this framework to work right now. Look at the very beginning of the jump, points A and B. At point A, the parachutist starts to fall. The speed is increasing rapidly, which means she's accelerating. But look over at point B. The speed is still going up, the line is still rising, but the gradient is getting noticeably less steep. The curve is flattening out. Applying our scientific reasoning, air resistance is building up. In examiner wording, the acceleration is lower.
Then we hit point C, stretching all the way over to point D. What's going on there? The line is perfectly horizontal. Now remember our quick win from earlier? On a speed time graph, a horizontal line means constant speed. In this specific physical context, this constant speed has a name, terminal velocity. The downward weight of the parachutist perfectly equals the upward push of air resistance. Because those forces are completely balanced, the acceleration is exactly 0.
Now this is where things get pretty intense. Look at the massive drop from D past E and all the way down to F. We have a negative relationship here. As the time on the x-axis ticks forward, the speed on the y-axis drastically falls. At D, the gradient is incredibly steep downwards, meaning we've got a high deceleration. By the time we hit E, the line is still going down, but it's flattening out slightly, so the deceleration is getting lower.
And boom, this brings us right back to our big question. What happens exactly at 35 seconds, at point F? The parachutist's speed flattens out again into a horizontal line, but it's much lower on the y-axis than before. This is your crucial examiner clue. She has reached a new, lower constant speed. Why?
Because her parachute just opened. That massive canopy skyrocketed the air resistance, slowing her down until the forces balanced once more. She hit a new terminal velocity, and once again, her acceleration is 0.
All right, I'm throwing a quick challenge your way right now to test these new skills. Scan the entire graph we just looked at. At which single point is the deceleration the absolute largest? Like, where is the change in speed the greatest? Think about what maximum deceleration looks like visually on this line. Lock in your answer in your head right now. Got it?
The correct answer is point G. Look at how incredibly steep that downward line is at the very end of the graph, dropping all the way to 0 speed on the x-axis. This is the exact moment the parachutist lands on the solid ground. She goes from her new terminal velocity to completely stationary in just a fraction of a second. The gradient there is the steepest negative slope on the entire graph, which means it's a massive, sudden deceleration.
So, let's transition into a bit of a writing checkpoint. Imagine you're sitting in the exam hall and this exact prompt pops up. Describe the parachutist's motion from 25 seconds to 40 seconds. This is the critical transition period covering points D, E, and F, where that parachute opens. This specific question is exactly where examiners separate the average students from the top band elite.
Just consider this flawed answer. She goes down fast and then slows down until she stops changing speed. That is going to get almost 0 marks. It's vague, it uses everyday language, it's just not physics. Now look at the top band, framework-driven answer. At D, she experiences high deceleration, which lowers at E until reaching a new lower terminal velocity at F. See the difference? Precise Cambridge wording. It hits on deceleration, the changing gradient, and nails the new terminal velocity. That right there is a full mark answer.
And honestly, that comparison brings us perfectly to the ultimate tip, pulled straight from an examiner's mindset. When a graph line changes, what new description or calculation is needed? This depends on the physical context. Never, ever just describe the math. Don't just sit there and write, the line goes up, or the gradient curves. You have to explain why the line goes up in the real world. Tie the ink on the page back to the actual physics happening in reality.
So, you now have the exact framework to decode changing gradients, spot terminal velocity, and build top-band answers with the right vocabulary. But here is the massive, unresolved problem staring you in the face right now. Having this framework in your head, it's entirely useless if you run out of time to actually write it down during the intense pressure of the real exam. Knowing the physics is only step 1. Executing it against a ticking clock is step 2. You need a system to draft these perfect answers in seconds, not minutes. Because ultimately, having all this physics knowledge in your head won't save you if you don't have a strategy to get it onto the paper before time is up. To get that strategy, click the video on your screen right now to master the timed answer writing system. And remember, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. I'll see you in the next one.